Hi, I'm Ben Pascoe. I'm a mechanical engineering undergraduate student here at U of M going into my fourth year. Today I'm here to talk to you a little bit about what I've been doing this summer as a part of the Summer Undergraduate Research Experience program. This summer I've been lucky enough to work with Professor Diane Bry, Dr. John Luntz, and current PhD student Julie Abel on an experimental study of active knits in a rib textile for Air Force applications. Now, the Air Force is constantly pushing the limits of aerospace research and development. One particular research interest is multifunctional structures that have the ability to dramatically alter their shape, functionality, or mechanical properties. One example is morphing aircraft that can adjust their wing geometry. And another application is active flow control, which varies texture across the surface. A third application is space deployable systems that can be deployed and reconfigured for surveillance operations. And lastly, they're interested in active membranes for flapping wing technology to mimic bats and birds. Now, all these examples require active structures with a growing need for distributed actuation capable of large, complex motions while maintaining the aerodynamic level of forces. Now, while conventional technology, such as electromagnetics, hydraulics, and pneumatics, come close to producing these necessary large forces and displacements, they have many drawbacks, including strong electromagnetic signatures, large size and weight, hydraulic leakage, and large infrastructures such as pumps or generators. Smart material-based actuators have held the promise of increasing actuation and decreasing the size and weight by an order of magnitude due to their high energy and power densities. They also can generate distributed actuation, which conventional actuation cannot directly accomplish. Unfortunately, though, smart materials by themselves have either very low strokes, resulting from material strains of only a fraction of a percent, or low forces, typically on the order of millinewtons and up to at most 1 Newton. Now, because of this drawback, the Smart Materials and Structures Design Lab is investigating active knits to meet their Air Force requirements. Now, all knitted materials are formed with two basic stitches, a knit stitch and a purl stitch, which are the inverse of one another, as you can see in the figure on the right. Combining these two loops allow for unique motions that are different from the contractile behavior of other traditional textile methods. First, the knitted textiles only use one strand of smart material, which allows the motion to propagate through the entire knitted fabric. Second, the loops are free to interlock with one another, which encourages or inhibits movement depending on the stitch. And third, the loops provide large curvatures that leverage the displacement of the actuator. This loop architecture enables a unique ability to create large and controlled motions. And one of the first things I did this summer was to learn to create these knit samples on a knitting machine and then investigate the behavior of some of the various stitch patterns. Next, I conducted an experimental study of one advanced type of stitch called the rib stitch to investigate the kinetic behavior and potential for creating surface textures, which is one of the Air Force requirements. Now, in this project, I used a knitting machine again to form the knitted sample in a rib textile by alternating knit stitches and purl stitches across the first row. Now, in each subsequent row, knit stitches are purled and purl stitches are knitted to create visible flat columns. Now, when actuated, this distributed accordion-like motion with large out-of-plane deformations can provide a controllable, three-dimensional texture needed for active flow control. Now, first, I designed and created a linear motion test rig, and then I experimentally characterized these rib textiles by actuating them with a heat gun, as you can see in the video, transforming the sample from a nearly flat sample to produce surface texture with rows of uniform ridges. As shown on the table on the left, the rib stitch provided promising results with single-stroke deployment actuation of nearly 4 times its initial prepackaged height under no load and about 2 times expansion under a 43 Newton load, which is about 4 kPa based on the initial area of the flat sample. Overall, the rib stitch samples are demonstrating about 100% strain distributed over a surface at about twice the aerodynamic pressures seen by many aerial vehicles under normal cruise conditions. Now, from beginning to end, this has been a very exciting experiment. We were able to create and investigate active knits using a rib textile to create a novel, three-dimensional distributed actuation behavior. Not only did this behavior appear interesting, but it performed at a high level as well, demonstrating the capabilities of producing high strains and moderate forces. These results are very impressive and can enable flow control applications in the future. Now, as a result of this research, I'm currently in the process of writing a conference paper for the SPIE conference that I'll be attending early next spring in San Diego, California. And after graduation, I plan on going to grad school and doing a master's program here at U of M. Overall, this summer has been a great experience. I've really learned a lot, and I would highly recommend the SURE program to any future students who are interested in conducting research, or anyone in general who's interested in gaining valuable lab experience and just learning more about the research process. Thank you.